Okay, we're back. So we just talked about systems in the body and how they help regulate fluid, or the main systems that help regulate fluid. And sometimes you might feel like, geez, I already know this, but that's good because that's just a refresher, reminding you of the things that are really important. Like your book doesn't even talk about the systems overall and how they contribute to fluid. I felt it was really important because it gives you a foundation. If you understand the systems and how they cause certain things to happen, if that system's broken, you can predict what's going to happen to the body. So if you know the heart contributes to fluid and electrolyte movement by doing certain things, if the heart's broken, you can count on those things not happening. Or if I tell you that the kidneys are important for filtering the blood and the kidneys break, you know that the body's not going to be able to filter blood. So I keep reminding you of the special processes of the systems, and you see some symptom or sign in a client or a patient that says, hey, they're not filtering, or hey, they're not getting circulation. You can look right to the systems and pinpoint. So now we're going to go in this section a little bit deeper. So we're going to go from the systems, we're going to go down to specific areas of the body that are distributing the fluids, or where they go. And this picture is just kind of a reminder of the different things that water is there for, like helping protect the tissues, chemical reactions to transport nutrients. Now we're going to go a little bit closer and actually look at the cells, the blood vessels, and the interstitial space, the space between. So some terminology you need to get familiar with. First is TBW, means total body water. So if you take all of the water in the body, the entire body, and you pulled every drop of water out and just left you as a pile of dust, where would that water be? Right? So our total body water is going to be roughly about 60% of us. So it's going to make about 60%. And down here on the bottom, I put a rule of thumb that you might want to remember, that 70 kilogram male, which is the average male according to medicine, 60% of our body is going to be water. So about 60% of that 70 kilograms is 42 kilograms. An instant conversion you can use is that when you see 1 kilogram, it's about 1 liter of water, or vice versa. So if we say that there are 40 liters of water in this person, that means about 40 kilograms of that person are water. So just kind of a rule of thumb to remember. So if you were to guess the total body water, and you said, well, there's the space inside the cells, there's the space between the cells, and then there's all of the plasma, where would you guess the most water in the body is going to be? Is it going to be in the cells? Is it going to be in the space between? Or is it going to be in the plasma itself? A lot of people automatically go for the plasma because we say, hey, there are roughly 5 liters of blood in a person. You can measure that. You can pour it into a container. But in reality, the bulk of all of the water in your body is in your cells. So 1 trillion cells in your body, each having this little tiny microscopic droplet of water, makes up the bulk of your body. We're going to call that the intracellular fluid, or the ICF. So just get familiar with the abbreviations. Everything that's not inside of a cell is extracellular. So the fluid that's inside the blood, the fluid in the space between the cells and the blood, that's all extracellular. Things like the vitreous humor or the aqueous humor in the eyes, that's extracellular, that's extra fluid. The fluid in your joints, do you remember what it's called? Synovial. That's extracellular fluid, it's outside the cells. So those are all kind of insignificant when you look at the grand scheme of things, but they're all really important at the same time. They have to be there, otherwise you'd have problems. But when we look at the extracellular fluid, basically it's any compartment. Lymph, synovial, intestines. What's CSF? Cerebrospinal fluid. Would you die if you didn't have any? Yes, and you'd have a terrible headache on the way there. So you need these different things. When we talk about the ISF, it means interstitial, which literally means between the space. So the space between here, like the Dave Matthews song. But this is interstitial. It's the space between the major areas. And then when we talk about intravascular, it means within the vessels. So don't forget, inter means between, intra means within. When you look at the distribution, like I said before, total body weight, male versus female, you can see that with males, we have just a little bit more water in our body. So not huge amounts, but a little bit more water. Women have a little bit more solid in their body. So if you take and you split up our body in proportions, remember this is proportional. So we're not saying that a 250-pound, 6'4" man versus a 5'2", 103-pound woman. You know, obviously this man has to have more water, but proportionally, per amount of water substance in their body, proportionally men will have more, women have less. And then when you subdivide these fluids, we can split into the intracellular, which is within the cell, to the extracellular. Remember, intravascular, interstitial, the aqueous humor, etc. So we can subdivide those two main categories into the interstitial fluid and the plasma. So a lot of people like to say, well, the plasma is where most of the water is in the body. But in reality, look at that. it actually represents one of the least amounts of the significant areas. So only about 20% of our water in our bodies in our plasma. And if you want deeper, looking deeper into the distribution, you can see a cell, one cell by itself is 85% water. Your liver, if we pull it out of your body, it's 90% water. When you look at the brain, where's the brain on here? It's like 80, there we go, 85%. So your brain is just a big bag of water and fats, basically. Even bone, 35% water. All right, so major factors that affect the distribution. First factor is going to be sex, and I already talked about this a little bit. So you can see a normal male is about 60% water, a normal female is about 50% water. If it's a lean male, 70% water, lean female, 60% water. But look at obese. So here's normal to obese. What happened to their water concentration as they gained fat? So in other words, this normally 150-pound person, when they go up to 180, what actually happened to the water concentration in their body? It went down, which is super significant, and I'll talk about it on the next slide too. But when you gain fat, that means you have to lose water. Do fat and water get along? No, not at all. Fat and water don't get along. So the more fat you have in cells, or the fat you have in your body, the less water you hold in your body, which means you're going to, I'll leave it to the next slide. A big thing to remember is that really after about 20% fluid loss, it's life-threatening. If you hit 1/3 fluid loss, so at roughly 33%, you better be really careful. These people better have an IV in their arm. Pediatrics, another thing. So babies, when they're first born, they're about 75 to 80% water. So a lot more water. And actually about 24 hours after postpartum or after they're born, they lose about 5% of that water. Right? So the big thing to remember here is that they're more susceptible to dehydration. When they start losing water, a large amount of their bodies are dependent on this high concentration of water, so they get dehydrated a lot easier. You have to think of other things like drugs that might be in the environment, foods that they might be eating, different type of things that may affect dehydration too. And then geriatrics, so the elderly population. With the elderly population, their body fluids start decreasing too. So as they start dropping, that means that they're more susceptible to dehydration also. They get more fat, like I said here. The more fat you have, the less water you have. They have less muscle mass, and muscles have a lot of water inside of them. Their kidneys don't work the way they used to, so they can't maintain water properly like they did before. And also the brain starts aging too, so the hypothalamus, the water detector, is starting to decrease. And like I said before, when you think of fat, and these are big areas of fat, pockets of fat, when you look at a fat cell, an adipose cell itself, you can see all of this fat, all of the water substance have to be smashed to the side. So the big influence here is that if you have more fat, you have less water, which means you're easily dehydrated, and you also don't move watery-loving substances through your bodies efficiently. Another trick is that fat-loving substances can hide in these fat tissues. So there's a huge difference when you're looking at body composition of somebody that's has more adipose tissue on them versus somebody that has more lean tissue like muscle mass. So those muscles like to hold water. But you have to remember that these people with more fat get dehydrated a lot easier because the fat displaces water. So how do substances move between those compartments? So you've got the blood, which remember is intravascular fluid. You've got the cell, which is the intracellular fluid. Intracellular fluid, and then you have the interstitial in between. So when you have control over somebody's body water, the only place you have direct control over is the blood. You put something in the blood, it has moved up by diffusion to the interstitial, and then by diffusion or pumps into the intracellular fluid. When you look at these body compartments, they move back and forth. If the blood's low in water, it will pull it from the interstitial. Then the interstitial is low, it pulls it from the cell, and vice versa. If the body's high, or the blood's high in water in the blood, it goes to the blood, to the interstitial, and then the interstitial is high, now it goes into the cell. Things shift between compartments, and the primary driver is actually diffusion, whether it's diffusion of particles or diffusion of water. Two keys to remember: when things are shifting, they try to stay electrically neutral. So when a positive moves across the membrane, a negative will go with it, or when a positive moves across the membrane, a positive will go the opposite way to keep it neutral. And we'll talk about this more in detail later. The other thing is osmosis. Water likes to distribute, so it's evenly distributed across the different compartments. So it's trying to hit equilibrium. So how do things move? I already said diffusion. Diffusion, the key to remember is that it's always passive, no energy required. The other thing about diffusion is it always moves down a concentration gradient. It will always go from high concentration to low. Things are crowded. They don't like being crowded, so they space out. It's like people. If you had a little room with 500 people in it and there were only 10 people in the hallway, people naturally want to diffuse out of the room and get out of there. Okay? But at the point where there are 250 here and 250 here, so they're evenly distributed, the movement's not that much. As a couple people start moving into this area, a couple other people will start moving back into the other area. So that's diffusion. High to low until it hits equilibrium. Some things can diffuse across the membrane. Oxygen, CO2, they can slide right through. Other things diffuse through little tiny pores or holes, and other things have to diffuse based on transport. So you might have a sugar particle out here, and it needs to get into the low concentration area, so it goes into the transporter, and it's like a little revolving door. It just kicks it in. No energy required. As soon as it sits in here, it just turns. Right? And then water. Water slides through things called water pores or aquaporins. The other type of movement is called active transport. And active transport requires energy. And typically when you see active, you're going to see the word pump. Like sodium, potassium, pump. Hydrogen, potassium, pump. You'll see calcium pump. So lots of pumps going on. That means ATP is required. Another process that requires energy is endo and exocytosis. So vesicular transport through the cell, moving that stuff out of the cell and ejecting it. Those are important processes you need to remember and how you can move things between membranes. Like, for instance, a protein. A protein doesn't easily slide through a membrane, so it has to be eaten, goes into the cell, and then it can actually be exocytosed out the other side of the cell. How we measure solutions, and this section is really kind of a basic terminology section, but how we measure solutions are kind of in three ways. So you have the osmolality, and the osmolality is talking about the number of particles per unit of weight of the solution. So typically when you see something like this, the 9% sodium chloride, this is actually an osmolality measurement. You might see it as milligrams per 100 milliliters or milligrams per deciliter. It's the weight divided by the volume. Right? Another way that they measure it is osmolarity, and it's the number of particles per unit. And the number of particles would be like when it says, well, down here, 300 milliosmoles per kilogram. So it's the number of particles per measurement. And another way we do it is milliequivalents. So milliequivalents, how these particles actually bind to hydrogen, which is a little bit more complex than you need for this class. And if you go into pharmacology or chemistry, they'll talk about it more. But when we measure, like we take a sample of plasma, we'll actually look at how many particles of sodium in a milliequivalents. So we don't look at your blood as 0.9% sodium chloride. Even though this is the same concentration of salt as the blood, we look at it in milliequivalents. Like we'll say you have 140 milliequivalents per liter of salt. So I put down here kind of rules of thumbs you want to remember. First, you want to remember that conversion of weight to water. So when you're talking about a kilogram of water, how many liters of water is that? So like when I just set up here, I forgot what I already said. So I said something like 300 milliosmoles per kilogram. Well, it's the same as saying 300 milliosmoles per liter. So it's the same thing. When you look at neutral saline solution, they have 9 grams of sodium chloride dissolved in 1 liter of water, and then the measurement comes out to 0.9% weight per volume, which is a measurement of osmolarity. So the 0.9% is what you want to remember. An isotonic solution, or a solution that's just like the body, will have 0.9% salt or saline. 300 milliosmoles is the measurement for isotonicity of the blood. That's taking into consider things like salt and potassium and chloride and all of these things. So that's neutral or balanced. And then as we go into individual particles, we'll talk about those individually, like I just mentioned before, 140 milliequivalents for sodium. Right. So why is it important? Because when you compare parts of the body, they use those measurements to compare. When you describe things in the body, very few things are like a standard and we just say it is because it is. It's like me asking, are you a tall person? Are you a short person? Are you old? Are you young? Is your nose too small? Is your nose large? Are you successful? Are you not? We rate all those things by comparing it to others. Are you tall? No, I'm not tall, but yes, I'm tall for my family. So are you short? Well, yes, I'm short for the average person, but I'm tall for my family. So we describe comparatively. When you're talking about solutions in the body, we do exactly the same thing. We compare. So here's some three general rules. First, use the inside of the cell as the reference. So if you're looking at red blood cells, the inside of the cell is the reference point. That's what you're measuring. If you're talking about a tissue, use the inside of the cell of that tissue as a reference point. Next, when we talk about the tonicity compared to the inside of the cell, we're referring to the solution around. Typically, inside of the cell, the tonicity is about 300 milliosmoles. It's actually 280 to 294, but we use 300 as an average range. So if this inside is 300 milliosmoles and this outside is 300 milliosmoles, they are the same, or iso. So this solution out here is what we're trying to describe. We know what the cell is. We're describing the solution around it. So tonicity describes the extracellular fluid unless it's otherwise marked. So isotonic means the cell is 300, the outside is 300 also. If you look at a solution that is hypertonic, hypertonic means more. Tonicity refers to the solute. So we're saying that this solution out here has more solute in it than inside the cell. If it has more solute, when we talk about osmosis, what's it have to have less of? It has less water. So if I take this 300 that was in here and I raise it up to 600, what did I just do to the water concentration? I reduced it. So that's telling me that the water here is low. The water in here is still, remember, the same. The 300 milliosmol, we're talking about high water compared out here. So the water races out and shrivels up the cell. The cell will shrink. It can't carry out its metabolic reactions and it dies. It's like shrinking bacteria to kill it when you cure meat. The second solution is hypotonic solution. So in hypotonic solution, I have less tonicity out here, so less solute out here, which means I have more water out here. Water wants to go from high concentration to the low, and the cell expands until it pops. You can try this with a raisin. I love cooking raisins in my oatmeal because raisins are shriveled up, right? So there's very little water inside of a raisin. But when you put it in the oatmeal with high water concentration and heat, that heat speeds up the diffusion. The water goes racing in, it swells the raisin until it's gigantic, and then when you bite into it, it pops. So kind of interesting, fun application to real world, I guess. So always remember what happens to a cell when you put isotonic solution around it, hypertonic solution, or hypo. The reason this is important is because if you put isotonic solution in somebody's blood vessels, that's going to do what to the cells? If it's the same concentration, the water is the same concentration as the cells, it should stay the same. If I put a hypertonic solution, so I put a really, really salt intense or dense with salt solution in somebody's body, what's going to happen to their cells? It's going to pull the water out of the cells. They shrink like a raisin. Right? If I put a hypotonic solution in somebody's body, that hypotonic means there's lots of water in that solution. It's going to race into the cells and swell them up. A good application for hypertonic is if you were stranded on a deserted island and you drank the salt water surrounding it. That salt is extremely high. It's hypertonic compared to your blood. So when you put that salt water in your GI tract, what's going to happen to the water in your body? It's going to be attracted to that salt water in your GI tract. It's going to pull out in your GI tract. It's going to dehydrate you and shrivel your cells up. And then you'll end up dying because of it. So think quickly here. We've talked about organs, we've talked about the cell level, and we've talked about some terminology. So first, let's say you just ate a big bag of pretzels or a big pile of these salty pretzels like this, which actually makes me kind of crave it. Right? You didn't lose any water, but why are you so thirsty? Think about this as a tissue level. Okay? What type of solution would this situation cause the blood to become? So all that salt's going into your blood is becoming iso, hypo, or hypertonic solution around your cells in your blood. Okay. It's raising the solute, which means it's becoming hypertonic. So when it's hypertonic, what's going to happen to your cells? They're going to start shrinking. So your cells at the cellular level start shrinking. Think about it a little bit deeper. As your cells start shrinking, your body doesn't want that because your cells could possibly die. Right? So what organs would detect the increased salt concentration? So salt concentration, we're talking about concentrations here, not volumes. Your blood volume might be just right, but you have high salt in it. Your hypothalamus. Your hypothalamus has those osmoreceptors that detect the change in concentrations. So now, what organ? I think I may have just said that. Hypothalamus has the osmoreceptors. So the hypothalamus is going to make you do two things. The first thing it's going to do is it's going to make you feel like you're thirsty. You're going to start drinking water. So you bring water in. What are you trying to do to your blood? You're introducing water to it because you have a lot of solute. You're diluting it down until it's isotonic again. Right? what other chemical will the brain release or the hypothalamus release to help you keep water in your body? Would it be aldosterone or ADH? It would be ADH. And this is kind of a key. You're trying to keep water. You release ADH because you're trying to keep water. Do you want to keep salt? No. You don't want to keep salt because you have too much salt in your body now. So will your body start releasing aldosterone? No, because aldosterone will make you retain more salt. So your body is going to stop releasing aldosterone and let you secrete it and get it out of your body. So ADH is released, but not aldosterone. So don't think of them always being released at the same time. In fact, the hypothalamus doesn't release aldosterone. The renin-angiotensin-aldosterone system does. So in other words, how would the kidney respond to this? Number one is the kidney would start retaining water, keeping water because ADH is telling it to. But the kidney will not release renin. So if it doesn't release renin, you don't turn on the angiotensin-aldosterone system, which means that you don't start releasing aldosterone, which means you're going to get rid of sodium. So the kidneys respond by letting the sodium pass straight out into your urine, but the water starts being retained. So what would happen to your urine? Would you be making lots of it? No, you wouldn't. You wouldn't be making very much urine. What would you know about the urine, though? It's going to be very concentrated. It's going to be very concentrated. It'll be a darker color, which is a sign that you're dehydrated. So just think of the pathways. Think of the cell. What's going to happen to the cell? What's going to happen to the tissue? What's going to happen to the organs? So overall, the result is increased water in the body, increased volume, but a decreased salt concentration because you're trying to bring it back to isotonic. Right, so the pathophysiology of dehydration symptoms, definitely remember the key is to dehydration. And what happens in hydration is that lots of causes can happen. You can be sweating crazy. You can have a fever, which causes you to sweat, which causes you to breathe heavy, to blow out lots of hot air. You know, it's full of water. Burns can do that. They suck water out of your skin. Hemorrhages, that's isotonic fluid loss. You're completely just bleeding the blood out. Vomiting, diarrhea, all good examples. So you can think of the different organs. And when you're thinking about the organs, make sure you know how they contribute to the fluid. Do they add fluid to the body? Do they take it away? What happens if you turn either of those up? What happens if you add too much water or you take too much away? Right? So anyway, you have these causes of fluid loss here. So what's going to happen to your blood? Let's say you're losing pure water. Not lots of solutes. What's going to happen to your blood? If you're losing pure water, the blood becomes hypertonic and it dehydrates the cell. What if you're vomiting or hemorrhage? Actually, a good example. Vomiting, hemorrhaging, you're losing electrolytes and you're losing water. What happens to the tonicity change of the blood? If you're losing electrolytes and water, the blood stays isotonic, but the problem is that you have less volume. So now it works on pressure. The low pressure in your blood pulls water and electrolytes from the interstitial fluid, and the low pressure in the interstitial fluid now pulls water from the cells. It's an isotonic change, but the problems, the outcomes are just as bad. You don't have water, you don't have moisture in your cells start drying out, they start shrinking. Right? So you can look at this as not being one specific thing, and that's why I left it blank. If you have different situations, like if you're urinating a lot of really dilute urine out, you're losing lots of water but not lots of electrolytes. So you'd be becoming hypertonic. If you're bleeding, you're losing isotonic fluids. So you can still get dehydrated, but it's isotonic fashion. So sometimes it may be confusing, but I left these blanks so that you can look at what is the primary cause and then work from there. Right? It's kind of like sweating. If you're sweating a lot, you're losing electrolytes, sodium, potassium, chloride, you're losing water. Okay? The blood's still isotonic, but you have very little fluid volume, which is your problem. Your organ cells will start shrinking just the same. So mild dehydration is when you lost about 2% of your body weight of water, so about 1 to 2 liters. Not talking blood, because 1 to 2 liters of blood is significant. When we're talking about 1 to 2 liters of water, we're talking about evenly distributed water from the body. So your skin starts getting a little bit dry, it might get a little thick. If you start pulling up on your skin, like pinching it, pulling it upwards, it might stay in that shape, and it's a sign that you're getting dehydrated. You might get really tired, you might start getting headaches, you're not getting good adequate flow and water to the brain, in other words. Right? And then constipation. Why would you get constipation? It's because the GI tract's trying to compensate and it's trying to pull more water in, which makes your feces more dense. Right? Severe dehydration is when it's over 5%, so about 3 to 5 liters of water is lost from your body. So at this point, you're going to stop sweating. You might be hot, but you're not going to be sweating, because why would you not want to sweat when you're dehydrated? Because you'd lose more water. So the body's trying to compensate, but now you have another problem. Your body's getting too hot. This low skin turgor is talking about pulling your skin up. It should snap back to normal shape. If it stays up, then that means you're dehydrated. And then if you keep pushing this over 20%, it's possibly fatal. When it's over 30%, you're dangerously low and you need an IV in your arm. And then, like I said, this is kind of like dense bulk information, but don't give up your thinking. When you have a situation, you have to run through your mind all the possibilities, eliminate the ones that don't work, and keep the ones that do work. So look at the problem. What organ's not working appropriately? And then here's the question for this set. Question number 3. So what situation could have caused dehydration due to the integument? What can in other words, tell me what the integument system could do that makes you lose a lot of water that causes dehydration. What could be happening in the kidneys that would make you lose a lot of water and become dehydrated? What's something that could be happening in the circulatory system that's making you lose lots of water that makes you be dehydrated? What's something that could be happening in the nervous system, maybe hormones or behavior you're doing, that would make you lose water? What would be happening in the GI tract that makes you lose water? So I'm hoping these all are making sense to you. And then for your own use, you might want to go back and say, well, what could be happening here that causes overhydration? Or how do you get the water? So hit the pause here. This is the last of this video set, or this video, and I'll see you on the next video.